Today we're going to cover H, P, and HP versions of the finite element method. And we're going to look at the theory behind these methods, hoping to get a priori and a posteriori error estimates that are going to tell us a little bit of how our solution or approximate solution is. Well, I am not going to go through the p-FEM in 1D we did last time, but essentially, as you remember, is basically building a better approximation by increasing the polynomial order of the interpolation inside the elements. Okay. The only thing that I am going to say is that if you look at the way the shape functions are organized, they are only non-zero at the ends of a node, the linear ones. But every high-order shape function is actually zero at the ends. Okay, so in that sense, the solution is being improved hierarchically over previous or lower order interpolants. In other words, if you have your linear shape functions only, well, the quadratic term is just going to improve quadratically the approximation inside the element. So it's added hierarchically to whatever the linear interpolation can do. Remember, the Galerkin projection, right, the Seas lemma, as you see in the paper, is going to do its best to reduce the error in that polynomial space, right? So that is, if I use a linear interpolant alone, right, that is the best solution can be for that linear interpolation. The moment I add the quadratic interpolant, right, then the same applies. So if I get a non-zero degree of freedom associated to that quadratic polynomial, then I am improving the solution, right? The best solution in that quadratic polynomial space and so on, okay? That's the only thing I'm going to say. The rest is all there, but now we're going to focus on some theoretical estimates on convergence rates. Okay, so as I said, we're going to look at H, P, and HP versions of the finite element method. Okay, so we have seen for h-FEM, for the H version, normally you have a linear or a quadratic interpolant. That is mostly what is used in practice. You would never go beyond quadratic. And let's say either 1 or 2, the polynomial order. And then, of course, what you do is you reduce the size of the finite elements in order to improve the approximation. So h tends to 0 in order to improve the approximation. And in this sense, the error is going to be given by the smallest or the largest element size? The largest, right? So that is what is going to control the error. In a way, it's the weakest link, right? Okay, we also saw last class the P version. And well, what we do is we keep our mesh fixed. And of course, in order to improve the approximation, we increase the polynomial interpolant. And therefore, the order is going to be dictated by the largest polynomial interpolation order in an element or the smallest one. Smallest polynomial order. Or there. Okay, so now I'm going to just give you a couple of examples which are in line actually with what you have to do for a project. So in my first example, I have a smooth solution. So if we have our, let me make this nicer. Okay, that is my body force. And well, we assume that AE is equal to 1, our axial stiffness modulus. Well, if we take a body force that is, let's say, this function, sine of 8x, so it's a trigonometric function, you can actually show that the exact solution for this problem has this form, 1 over 64 sine of 8x plus 1 over 8 cosine of sine of 8 times x. And well, I am just going to show you how this looks, and I'm gonna copy this here. Yeah, and you see that it actually looks very smooth, right? So it's similar to the problem that you have in the project. Remember that in the project we have a body force that we actually control with a parameter, and depending on that parameter, the solution can be either very smooth or non-smooth, right? There is a when we take that parameter and we make it very high, then we get into a close to a discontinuity, right? A very sharp gradient solution. Right. For here, for this problem, you can see the solution is very smooth. And so if you plot the error in the energy norm as a number of degrees of freedom, actually I'm gonna plot the log of that. E is the error in energy norm, right? As a function of the log of the number of degrees of freedom. Well, it turns out that how do I do this? Okay, I'm gonna do it like this. It looks something like this, where this one is the h-FEM, and this one here is p-FEM. So in log-log space, right, the H version of the finite element method is going to give you a straight line. For a smooth problem, that is the theoretical behavior of the finite element method. And for p-FEM, the convergence is actually going to improve with the polynomial approximation order. So we actually have fancy names to say the same thing. So h-FEM gives what we call algebraic convergence rate. And that essentially just says that the rate of convergence, which is given by the slope of this line, is constant, right, regardless of the number of degrees of freedom. On the other hand, p-FEM gives what we call exponential rate of convergence. And as you can see, that basically means that the slope is actually changing with increasing number of degrees of freedom, which essentially is telling you that the more you increase the polynomial interpolation, the error is going to be reduced faster. Yeah? Okay. Okay, so that is for a problem with a smooth solution. But what happens when you don't have a problem with a smooth solution? So let me just copy this. Bless you. So let me make this problem 2. And now this is going to be non-smooth. And I'm going to choose another body force. Let's say b of x is lambda times lambda minus 1 multiplied by x to the power of lambda minus 2. And that doesn't look like a lambda here on top, so yeah. And well, lambda is just a constant that is specified by the user. Well, the exact solution for that problem is minus x to the minus lambda plus lambda x. And here you have the solution for lambda equals 1/2. And you see what happens. As I get closer to the origin, the solution actually goes to minus infinity for this problem. Yeah, and so there is what do we call this when something goes to infinity? Singularity. We have a singularity. Now there are singularities and singularities, right? There are singularities that are stronger than other singularities. So this one is not really that strong. Let's say this is going to be a mild singularity, right? That basically means, well, the singularity is confined to a point in our domain. So away from that point, the solution is actually well behaved. Okay? Well, for this type of problems, and I'm going to copy this again. Oh. Yeah, well, it turns out that h-FEM still gives you an algebraic convergence rate, but now the difference is that p-FEM also gives you an algebraic rate of convergence. So this is no longer a curve. It's going to look more like this. Okay? Now, notice that I start drawing these curves from the same point because, of course, for a linear interpolant, the p version of FEM with a linear polynomial is going to coincide, right? Those are spanning the same finite element space. Okay? So that is the difference. So both okay. Okay, so you may argue, well, how do we improve the solution of p-FEM? Or how do we get a better approximation if I know that for problems that exhibit a singularity, I get algebraic convergence with p-FEM, right? Any ideas? So if I keep my mesh fixed and I just increase the polynomial interpolation order, I know that I'm not going to get exponential rates anymore.
You change the mesh size and you.
Yeah, and that's exactly what the HP version of the finite element method is. So you take the best of both worlds. You take the best of h-FEM and you take the best of p-FEM. So what we do is we reduce the size of elements as we're getting closer to the singularity, and we also reduce or increase the polynomial interpolation order as we're getting close to singularity. Reduce. Okay, think about it. Well, you actually want, remember that polynomials are highly oscillatory interpolants. So where the solution is not really very well behaved, you don't want that to happen. And therefore, away from the solution, right? Away from the singularity, where the solution is actually smooth, you want to use the capability, the main capability of p-FEM, which is, okay, I increase the polynomial order and I get a better solution. But closer to the singularity, you're basically shifting to h-FEM, lower polynomial interpolation orders with smaller elements. That's all it is, okay? So you can actually retrieve back your exponential rate of convergence if you nicely apply this idea. So one may argue, well, so then how do you do that, right? In what order or what is the size of the elements that you have to place closer to the singularity in order to recover that exponential rate of convergence? And this was studied by Babuška, by Szabó. In fact, in the book of Szabó and Babuška, this is very well described. And there is an optimal geometric factor for defining the size of elements so as to get the best convergence rates when you have this type of singular problems. So I'm going to, let's say this is your domain, and this is going to be your first element, second element, third element, and then the other one is the last element. So here we're going to use p equals 1, here p equals 2, and for instance here p equals 3, and here p equals 4, right? And then, well, the elements are such that the first element has length. So if this is the length L, the first node is located at LQ cube. This one is at LQ square, and this one is at LQ. And that Q is called a geometric factor. And by just doing experiments, it was obtained that the optimal value of Q was squared of 2 minus 1 squared, which is approximately equal to 0.17. And well, in practice, Szabó and Babuška say that in practice, using just a factor between 0.1 and 0.15 works very nice. You still get exponential rates of convergence. Yeah. So the way the nodes are, and keep in mind that all of this is in 1D. In 2D things are different, but it's really out of the scope for the material that I'm going to give you in this class. So xj plus 1 is going to be equal to 0. So that is the locations of the node if j is equal to 0, or L to the q, number of elements minus j, and then j equals 1, 2, etc. number of elements, which is just repeating what I say here. So what are the locations of the nodes? And so with this HP extension, so combining H and P versions of FEM, we actually recover the exponential convergence rate. So let me write this down here. Okay. Okay, so all of this has pushed researchers to classify the problems in 3 different categories based on how the solution actually behaves. So that is what we're going to do now. We're going to provide some initial classification. Actually, it's more involved than that, because in each one of these classifications you can have sub-classifications depending on how singular your solution is, as I discussed. But we're not going to get there. Again, that's out of the scope. But based on the type of solutions that you can have, right, you can define 3 different categories of boundary value problems. Based on regularity. You will hear that term in works that talk about this. So regularity is essentially how smooth your solution is, right? So if your solution is very smooth, you can say also the solution is quite regular. So regularity is a term that is used. So we're going to classify these problems in 3 categories. So category A. In this category, U is analytic, your exact solution, in your domain, of course. We're only interested in solving the solution in our domain. And that just says that the solution can be expanded indefinitely in Taylor series. We're going to have another category. You may guess is category B, where the solution is analytic almost everywhere, except at some regions, and those regions have to be very small. In other words, so small that they form what mathematicians call a set of 0 measure. That is essentially a point in 1D, it's a line in 2D, or a point and a line in 2D, and a point, a line, or a surface in 3 dimensions. So a surface in 3 dimensions has no volume. A line in 2 dimensions has no area. So all of those are sets of 0 measure. So as long as our singularity is confined to a set of 0 measure, then those are the problems that are in category B. And as you saw already, the convergence rates for the P version of FEM are going to be algebraic or exponential. Algebraic, right? So U is analytic. In omega, except in a finite number of sets of 0 measure. And then finally, well, by extrapolation, you already know what I'm going to say, right? So there is a third category. And who can tell me what are these problems?
What is without solution?
Huh?
Without solution?
No, you still have a solution.
It's not 0 measured.
Well, yes, or essentially you can say, well, if I have a problem that is not in A or B, I can put it in C. Pretty much every single other problem that is not in these 2 categories, I can put them in C. And of course, those are the ones where, the solution is actually singular, not in a set of 0 measure, of course, right? So U is not in A nor B. So now that we have this, and we know how the methods behave theoretically, at least qualitatively we understand that h-FEM is going to give you algebraic convergence rates always. p-FEM may give you either exponential rate or algebraic rate, depending on how the solution behaves, the regularity of the solution. And of course, based on the regularity of the solution, I'm going to be able to place that problem either in category A or B, right? And therefore p-FEM may give you an algebraic rate if it is in category B, an exponential rate if it is in category A, right? Of course, qualitatively we know already how these methods behave. Now let's try to see in formulas, because that is basically what the convergence rates are obtained from, right? So how do we express mathematically these curves that I described here? Okay? And that takes us to what is called a priori error estimates. So if you take h-FEM, then the algebraic convergence can be expressed like that. So you have, remember that we define at some point the norm in the energy space. So I'm going to call it like this, the energy norm of the error. See, inside I have u, which is the exact solution, and I have UH, that is the approximate solution that is returned by the finite element method, right? Well, this error is bounded by some constant, I'm going to call it that C1, and by the mesh size to the power of beta H. Beta H is my convergence rate, right? It's the slope of that straight line that I draw in log space, multiplied by the norm of the exact solution in the energy space. So again, C1 here is a constant that is independent of U and H. H, we said, is the maximum or the minimum element size? Maximum. And then beta H is the rate of convergence. That is dependent on the polynomial order that we are using, P, and of course the regularity of the solution, U. That is for h-FEM. Now in p-FEM, of course this expression makes absolutely no sense. Why? The mesh is always fixed, right? So in p-FEM we have to change the algebraic type of error estimate to include something that is intrinsic to p-FEM, which is the polynomial order. And so this expression is going to read, let me just bring that, separate a bit more. The error in energy norm, again, now is going to be bounded by some other constant, C2, divided by P to the power of beta P. So beta P is now my rate of convergence for the p-FEM times the norm of the exact solution. Of course, again, in the energy norm. Yeah? So here, of course, C2 is going to be another constant, but P is the what? The minimum or the maximum polynomial order? Minimum. Yeah. And keep in mind that, of course, you can rearrange this term. So if I take this here, this term here, and I send it to the other side of the inequality, then, of course, you have a relative error in the energy norm. And actually, this is the way sometimes we compute the error when we are solving the problem, right? normally we compute a relative error in energy norm. So we actually have the exact solution, and sometimes you can do this by integrating this quantity over the element. And again, it's a relative error. So it's the exact solution minus the approximate solution divided by this term here. And you get a relative error. Okay? Okay, so these are the algebraic estimates. And the exponential estimate that, as you remember, is obtained for p-FEM in problems in category A, or actually those problems in category B, if we apply this idea of using the HP extension, we can actually also recover exponential rates of convergence. Yeah, let me finish this and then I'll ask. Okay. Yeah. So for those problems, again, either p-FEM or HP, yeah. So now the error in energy norm is going to be bounded by some constant divided by e to the power of gamma n theta, and n here is the number of degrees of freedom of the problem. Remember that when let me finish this and I'll discuss this. When we have h-FEM only, it makes sense to talk about the mesh size. When we have p-FEM, it makes sense to talk about the polynomial interpolation order because our mesh is fixed. But in p-FEM, we also like to think of in terms of number of degrees of freedom, right? Because the more the polynomial interpolation order, the more the number of degrees of freedom. And normally, right, we do plot errors in energy norm as a function of the number of degrees of freedom. Well, here's the case. So that is why the exponential rate, the exponential estimate is expressed in the number of degrees of freedom, right? Yeah. So here, gamma and theta are constants. We will see in a minute that if you basically take your error and you apply the logarithm twice to that error, then you are going to get a straight line with the slope of theta. And so there are also theoretical predictions on what is the value of that theta. And n here is the number of degrees of freedom, total number of degrees of freedom. Okay? Yeah, you have a question?
Yes. What is meant by the minimum of no order?
Yeah, because we are trying to set some theoretical predictions on the value of our convergence rates, right? So if you have, let's say you have a mesh where you are distributing so it's not uniform the value of the polynomial interpolation order. So you may have elements with p equals 1 in some part of your domain, and in others you may have a higher order polynomial interpolation order. Well, you would expect that the error is actually dominated by the elements where you have the smallest polynomial interpolation order, right? Because that is where the solution is supposed to be the worst, in the lower interpolation order, right? That's why in p-FEM, since our mesh is always fixed, well, you have to always look at what is the weakest link, right, in improving the solution. Well, of course, in p-FEM is always going to be the elements with the smallest polynomial interpolation, which is 1, right? Yeah. So in p-FEM, if you have elements with p equals 1, well, the error should be higher there. And it's actually nice because when you program all these things, you can actually also get to visualize the error per element, right? So I can do this computation. I can compute this relative error in energy. Of course, I need to know the exact solution, right, to do all of this, right? Because then, if I know the exact solution, well, I can compute the error, this guy, relative, so I divide by this guy, and I can plot a quantity per element. And this is super nice to visualize where the error in your exact solution is. With respect to the exact solution I meant, right? Yeah?
What do you mean with the energy norm?
Well, that goes back all the way to the first lessons, but if you remember, we defined the energy space, right? That is comprised of functions that have finite strain energy. And we say, well, that space we can actually quantify in a way the error, and we defined the norm, right, as a measure of quantifying something in that space. So similarly to what we do in Euclidean vector spaces, right, where if I take the norm of a vector, right, I am able to quantify the length of that vector. Well, in functional spaces, like the ones that we use in the finite element method, the energy norm is what we use to quantify, right, to assign a value to something. So we measure things in functional space by defining an error. So if you go back all the way to the, I think it was the second or lesson or the first lesson, we defined that the norm in the error space, sorry, the error, I'm completely lost. The norm in the energy space, right? You have to basically apply the square root of the strain energy, if you remember, right? So we compute the strain energy, we take the square root, and then that gives you the norm.
Is it the same as?
It is the same. It is exactly the same. And we will see in a minute, because when we want to approximate that value of the energy, right, we use those ideas to solve a nonlinear equation so that we can actually predict what is the value of our exact strain energy. Yeah, but yeah, we looked at those concepts very early, so we can discuss it further later, so I can scroll back, but let me finish with this part. Yeah, yeah.
The beta h, is that beta times h, or is it like some sort of h?
Beta h is a bit, no, it's beta h. So beta h is just one quantity, right? Right. We call that, and of course we call it a subscript h, just to mention that is for the h-FEM.
And theta, is it n to the power theta?
Yeah, n to the power theta. Yeah, so it's e to the power of gamma n to the power of eta. So eta is basically a second exponent. That's why if we want to know what the value of theta is, you have to apply the log twice. And we will do that in a minute. Okay. So going back to those curves, now let's try to see how they look like. So let's define our relative error in the energy norm as u minus uh, again, energy. So the energy norm of the error divided by the energy norm of the exact solution. This is, all of this is going to be called E subscript E energy. Okay, that is my error, relative error. Again, relative because I'm dividing by the norm of the exact solution as well. So then if you do that, and you basically take a look at the first equation that we looked at here. I'm looking at this equation, so I basically move this guy down. Yeah, and I'm going to apply the natural logarithm twice. So I get that the natural logarithm of that quantity is going to be bounded. Of course, you know that you apply the natural logarithm to the product of two things, then it's the natural logarithm of the first quantity, which is my constant. I don't know why I put this guy, is not needed, plus beta h times the natural logarithm of h. And if you see this, and that is why we saw earlier that in log-log space, that was the equation of a line, where that pretty much looks like the equation of a line in log-log space, right? Right, so you can say, okay, this is y, right? And this one here is x. Well, this is just going to be a constant that is going to shift that straight line up or down, and then this beta h is the slope of that straight line, okay? And so I will borrow again that curve so I don't have to do it again. Oh, So that is going to give me a slope, and again, I'm going to change the slope to a positive slope because this is h. Before it was the number of degrees of freedom, and of course you would expect as you increase the number of degrees of freedom, you expect the error to go down, right? So now that curve for h-FEM, and I think we used red for h-FEM, is going to look something like this. Okay? That is beta h. Yeah? So that is our first curve. Let me bring that up. Actually, also, you could say, well, what if I want to express, we were talking about the number of degrees of freedom. So what if I want to express, instead of the log of h, I want to just compute the error as a function of the number of degrees of freedom? Well, you can say that since h is approximately equal to 1 over the number of degrees of freedom to the power of 1 divided by d, is the dimensionality of the problem. This is for regular meshes, okay? Only for uniform meshes you could claim this is true. Well, and we can basically put this guy, we can put it here. Well, what you get, and I'm just going to copy this again, copy. Then now, well, let me give some space here. Now I'm going to get this guy and these guys. I'm going to change the sign of this, and then this is going to be divided by d. And then is the natural logarithm of the number of degrees of freedom. So I have only inverted the slope if I express this in terms of n, right? So essentially, let's do this again. Actually, let me just put, there is a missing e here. So this is going to look slightly different. So now, as I am increasing the number of degrees of freedom, which we call n, right? This is going to be a line that looks like this. And then the slope of that line is what? Huh?
Beta h.
Yes, it's beta h divided by d. And this is very good to know. And this has actually been a problem in previous years with students, because you are asked in the project to compute error estimates as a function of the number of degrees of freedom for the two-dimensional problem. That is the second problem. And people are super confused. Now that I am expressing in terms of n, right, and not h, so then what is the rate I should get? And they get a rate, and yeah, some people think it's not optimal or close to optimal, but they don't understand. Well, you just basically, the theoretical prediction that you have, you just divide it by the dimension of the problem. So if an optimal convergence rate in 1D is equal to 1, if I express that in terms of the number of degrees of freedom, optimal convergence is going to be what? It's going to be 1/2 in 2D, but it's going to be 1 also in 1D, right? So in 1D you get the same rate, but in 2D you have to halve that rate if you express it in terms of the number of degrees of freedom, because of this expression here, right? And this happens only for uniform meshes. Uri, you have a question?
Yeah, it says like h is equal to 1 over n rd.
N to the power of 1 divided by d. So d, I should put it here somewhere, that d is the dimensionality, because when you are actually looking at these notes, dimensionality. Yeah, n to the power of 1 divided by d. Okay, so that is for the first class where you have algebraic convergence rates, and we have expressed both in terms of h and in terms of the number of degrees of freedom. Okay. A second type was, of course, the polynomial rates. So we're going to get back to algebraic rates, but when we're using p-FEM. Remember that these are for category B. Remember, p-FEM gives you back algebraic rates when the solution is no longer smooth everywhere, okay? And so if you remember the expression, it was bounded by C2, right, divided by p to the power of beta h. Well, if we apply log to that expression, what we get is this expression here. So similarly, it's actually very similar to this curve. Okay, we just have to replace this guy by p. And this is pp. And again, these are natural logs, okay? I just write log, well, you know, a mathematical log is actually the natural logarithm. But in any case, all logs are one constant apart from one another, so they are equivalent if you just look at the slopes, which is what we are interested in, okay? Okay, so this is for the second type of, so when you look at polynomial, but what happens when you look at exponential rates? So that is basically 3. And now our estimate looks like this. It's going to be bounded by the logarithm of that constant minus gamma n to the power of theta and the logarithm, the natural logarithm of this guy, which is equal to 1. Right? That is what happens, but I'm actually interested in this guy. Because you saw that if I basically look at the exponential rate of convergence, well, I get a curve that looks like this, right? So applying log to the error doesn't really tell me much because, well, what is the behavior of p-FEM in that particular case? I'm not interested basically in the rate at a particular number of degrees of freedom. I'm interested in how fast that rate is. And in exponential rates of convergence, how fast the solution decreases is obtained by this parameter that I have here. This is the guy that I'm interested in. So then we can apply the natural logarithm again to this expression, right? And we're going to make an assumption, and the assumption is, well, as long as c is equal to 1, I'm going to get rid of that term because the inequality is still going to hold. That's all we do, right? So if we apply the expression again, well, what we get is the natural logarithm of the natural logarithm of e is going to be bounded by this expression here. And now, if you see, this is the expression of a line. So if I plot the natural logarithm of the number of degrees of freedom in the x-axis, and then I essentially apply the natural logarithm twice to the error, then I should get a straight line. And in the book, you will see that in an actual example, where we are obtaining that estimate for theta. So it has also some theoretical predictions. Yeah. I think for optimal, theta has to have a value that is 1 over d at least, and then you get a really great rates. Okay, and well, let me just put one last plot, and then we're going to close this, and we're going to go to the questions in a second. Okay. Okay. So here, this is going to be n, and this is going to be log again, and this one here is going to be theta. Something like this. Okay, so to summarize all of this in a table, depending on the problem, so we have category, and then we're going to have the H version of FEM, the P version of FEM, and the HP version of FEM. And we're going to list category A. For category A, which has problems that are smooth, right? Solutions are very smooth, very regular. So if you remember, H is going to give me what type of convergence? Algebraic convergence. So I get algebraic convergence. And the convergence rate is actually going to be equal to the mesh size. Sorry, to the polynomial order that we use, polynomial order. So in h-FEM, if I use in 1D, okay, I use polynomial interpolation order 1, in the energy norm, I should get what convergence rate? 1. If I use a polynomial order 2, 2. And this is energy norm, okay? Energy norm. Remember that the energy norm takes into account the gradients. So we compute the strain energy, right? We're actually computing using derivatives, okay? If we actually look point-wise at the solution and we're only interested at the values and not at the gradients, the convergence rate is actually double. And we're not going to look into that, but that is essentially called the L2 norm of the error. You can compute different norms of error, of course. We are interested in energy norms, but you can actually have L2 norm, and you can have norms of the error in sublab spaces. You can have the H1 norm of the error, H2, and so on. So there are many ways to quantify errors. Where in this course, we're only going to be looking at energy space. Okay? So for this, let me bring this back here. The convergence rate is going to be equal to P. Okay, problems in category A with the P version of FEM gives you what type of convergence? Exponential convergence. Yeah, and as I said a minute ago, you actually can have a prediction on the value of that theta constant that gives you the rate in when you apply the log twice. Theta is actually, for smooth problems, is greater than or equal than 1 over d. And HP version of FEM obviously is going to give you what? Exponential. Okay, now we're going to problems in category B. Remember, category B are nice, but there are sets of measures 0 where the solution is not nice anymore. You have a singularity. And we said, well, what is the behavior of h-FEM? Algebraic. But now the rate of convergence for this type of problems is going to be different. Because now we're looking at the regularity of the solution, okay? We're not looking, the solution is no longer smooth. So we have to try to understand how regular the solution is, okay? And therefore, it's going to be equal to the minimum of either the polynomial interpolation order or k minus 1, and I'm going to say in a minute what that is, or P, and this is for an optimal mesh. And K is the regularity of the solution. In other words, let's try to analyze what happens. When our solution is super smooth, this value of K is very large. That's why it doesn't get into the estimate in problems in category A. It's always going to be bounded by P. Yeah, because of course in h-FEM we just look at linear or quadratic, right? But when the solution is very smooth, this value of k, which is actually the exponent in the Hilbert space that you use, right? That is where our solution lives, is the exact solution, is super, super, super high. Now, when the solution is not so smooth, then that value of k goes down. And in fact, for instance, for a crack, or no, if I remember, for an L domain where you have a singularity in the corner, right? The exact solution lives in h to the power of 1.5. You see that for that problem, that is actually something that you would encounter in many problems, right? We always have corners like this. The solution is already not smooth anymore. There is a singularity there, right? Now, k, which is the regularity of the solution, or the order of the Sobolev space, goes down to 1.5 in that case. So now I have to look into this, right? Yeah? So, just to summarize, when our solution is not smooth, right, we have to pay attention at what is the regularity of the solution, what is the Sobolev order where the solution lives, and therefore our convergence rate is now going to be limited by that. So in that particular case, if I use a polynomial order of equal 1, and I know that k is going to be 1.5, what is going to be the convergence rate? Not 1. Huh? 1/2. You see that? You have a question? Yeah?
So basically, if k is low, it doesn't make any sense to have quadratic elements.
Yeah. Yeah, if k is low, then you have a problem. If k is low, right, like for example, you have a crack, then that k is going to be also small, and therefore there is nothing you can do that is going to give you a good convergence rate, right? In fact, for a crack in 2D, your rate is going to be halved, right? So in 2 dimensions, instead of getting 1/2 for the convergence rate, remember that optimal convergence was 1 versus the number of degrees of freedom. When we put that as a function of the total number of doves, sorry, I'm so much stuff. If I plot the error norm, right, in energy space as a function of h, the mesh size, optimal convergence is equal to 1 in 2D, right? Remember the polynomial order. Now, if I express that with respect to the number of total degrees of freedom, right, then that is going to be halved because I'm in 2D, so it's basically 1/2, right? If I want to solve a problem with a crack, that rate is going to be even reduced. So for that particular problem, it's 1/4, it's 1/4. So then the question is, how do you do, right? What do you do to improve the convergence rates for those problems where you know that there are singularities? And well, there is a lot of theory on this, and this is one of the bases for enriching your finite element space with singular solutions, right? The moment you do that, you recover optimal convergence rates because you are incorporating into the solution a singular function, right? And then when you do that, then of course the Galerkin projection is our friend again. It's going to minimize the error with respect to that space, and then we recover optimal convergence rates again. Yeah? Yeah, you have a question there?
Yeah. What is k?
K is the regularity of the solution, and you can, it's basically the order of the Sobolev space your solution lives on. Yeah? Some abstract mathematical. But just to make it very simple, if k is super large, right, your solution is very smooth. If k is very small, then you have a singularity. As I said, the solution for this L-shaped problem where you have a singularity because we have a corner, right, that solution, the exact solution, lives in h to the exponent 1.5, right? So now my convergence rate is going to be limited by that singularity. Therefore, I'm going to get a value of 1/2 only for the convergence rate in that problem. And this is for h-FEM, huh? This is for h-FEM. Okay, what happens with p-FEM? Let's continue getting this table. So for category B, you remember what p-FEM is going to give you? Algebraic convergence rate. And the rate that you're going to get, there is also, sorry, it's beta p now, is equal to 2 times k minus 1. And this is for uniform meshes. Again, bounded by our solution. Where does exact solution, where the exact solution lives? What is the Hilbert space? And well, for HP, what did we say with HP? Exponential, right? Because we can tailor the mesh and the polynomial order to recover that exponential rate. So I'm going to copy this. But now this theta parameter is going to change value, and it's going to be equal to 1 divided by 2d minus 1. Yeah. Okay. We have problems in category A and B, and then we're missing category C, which is the worst, right? And all we can say about this is that those problems can actually still be solved, but we can only say that the rates are positive. So, you know, you can still reduce the error. There is no beta H here, and this is beta P. So all you can say is that you can still use these methods to solve a problem. So as you reduce your mesh size, you're going to get a better solution, right? But that is as much as we can state. So just to complete the table, I'm going to add here some footnotes. So D, again, is the dimensionality, the dimension of the problem. And then K is the order of the Hilbert space. U lives on, so where U is. Regularity, we call this the regularity of the solution. Yeah. So for A, U belongs to HK of omega, and K is actually very large, as we said. And because K is very large, it's not going to control the convergence rate for category A. However, for B, as we say, U belongs to HK, but now K is greater than 1. We said in that L corner, K is 1.5. Actually, it's 1.544, something like that.
Doesn't it depend on where you are?
Sorry? Sorry?
Doesn't the K value depend on your location in the solution? So if it's very far away from the singularity, does the K change?
Yeah, but keep in mind that as we discussed this weakest link, right? There is still going to be a portion of your domain which is going to be dictating the error. So you can have, let's say, a very smooth. Your solution may be very smooth in lots of parts of your domain, but your convergence rate is still going to be dictated for the in the part where you have the singularity. Yeah. Okay. Quite some mathematical ideas. You had a question before, right? No? Yeah? Sorry, I wrong timing for the...
I wanted to ask
Yeah.
about the base of the logarithm.
Yeah, I already answered that, right? So we're using a natural logarithm, but again, those all the logs, the base doesn't matter because they are equivalent up to a constant. Yeah. Any questions? A lot of theory today. Yeah.
How can we compute the k for the exact solution of the assignment?
How you can compute k?
Yeah.
Uh,
What is different values of k?
Well, if you think about it, now that we have a tool, a numerical tool, to compute a solution,
Okay.
you can get a.
K.
You can get well, you can answer me that question actually. Go ahead.
Maybe by calculating the error, the algebraic convergence of the error. And then
Well, you see it in this table, right? There are some problems when you have singularity that are going to be dictated by this expression, right? So for those problems, the convergence rate is actually in a way telling you what is the order of the Hilbert space the solution is on, right? Now, of course, there is a lot of theory behind this, and there are exact solutions for many different types of problems. So you have asymptotic solutions for cracks and all different configurations, and then you get those analytical solutions. And if you have the analytical solution, well, you know where your what is your Hilbert space order, right? But numerically, you have already a means to determine how smooth is the space where your exact solution is. Okay. All right. Let's stop here. Before we go to a posteriori error estimates, let's make a quick pause, and then we continue in a few minutes. 5 minutes?